Welcome back, everyone. In this lecture, we'll go over the solutions for the convolutional neural network exercise questions. Let's get started. Okay, let's begin by running this first cell. And then once that's done running, we'll go ahead and create the data loaders. So I'm going to create two data loaders, a training loader and a test loader. So let me fast forward in time. Oh, looks like it's done now. So we'll go ahead and say our train loader is equal to data loader, pass in that training data, set our batch size to 10, and for the training, we want to make sure we shuffle that. And we'll do the same for the test loader. In fact, I'll just go ahead and copy and paste this, since it's going to be so similar, and change the train to test in both these cases. And then for the test data, we don't need to shuffle that, so we can say shuffle is equal to false. Okay, the next task was to examine a batch of images. We can grab a single batch by simply saying for images, comma labels, in train loader, and we'll just go ahead and break. That way, if we take a look at images, the shape of it, this is a single batch. It's 10 images, where each image is a grayscale image, so one color channel, and it's 28 by 28. We'll have to remember that order of the axes, because in order for Matplotlib to display it, we'll have to rearrange it a little bit, as we've done before. So we will say im is equal to make grid, pass in the images, and if you want, you can specify the number of rows. Then we'll say plt figure is equal to fig size. I'll say 12 by 4. And then finally, so we'll say plt im show. We first need to transpose this. So we'll say transpose m.numpy. And then we'll also say 1, 2, 0. Just as we previously discussed, you have to reorder those axes. Run that, and then you should see a batch of images here. It may not be the exact same batch due to the fact that we're randomly shuffling these up here, and we didn't actually set a seed. But you should see 10 images. All right. Next, for downsampling, basically the question asks if a 28 by 28 image is passed through a convolutional layer using a 5 by 5 filter and a step size of 1 with no padding, what is the resulting matrix size? So, with your 5 by 5 filter, that's going to leave a 2 pixel border on each side. So that means the overall dimension is reduced by 4. So the resulting dimensions should be 24 by 24. And we can confirm this by running this code below, and we see here our 24 by 24, essentially losing 2 pixels on each side due to the size of the filter. Okay, next question, if the sample from question 3 is then passed through a 2 by 2 max pooling layer with a stride of 2, what is the resulting matrix size? So this one's pretty easy, you're just going to divide by 2, so you have a 12 by 12. And there it is, 12 by 12. Okay, next let's go ahead and define that convolutional neural network. So what we're going to do here is begin by setting up our convolutional and pooling layers. We'll say self convolutional layer number 1 is equal to, and here you have a lot of flexibility as far as what actual values you want to choose, but we'll do as we've done before, 1 color channel, 6 filters. We'll do a 3 by 3 with a stride of 1. Then for the next convolutional layer, we'll say, again, convolutional 2D, incoming 6 filters, expand that to 16 filters, take a 3 by 3 kernel with a stride of 1. And then finally, if we do this math, so fully connected layer, this is going to be just as we did before in the regular MNIST dataset. That results in a 5 by 5 times 16 incoming dimensions. We'll reduce that down to 100, and then we'll further reduce that down in the next fully connected layer, so nn.linear to 100 to 10. And then let's go ahead and set up our forward function. So on the first pass, the data goes straight into that convolutional layer. So we say self.convolution1, pass an x there. Then after that layer, we take that result and pass it through a pooling layer. So we'll say max underscore pool 2D, pass in that x, and it's a 2 by 2 filter with a stride of 2. And then we're essentially going to repeat this. So I can just copy and paste this, put it down here, but I just need to specify this is now the second convolutional layer. And after that, we need to reshape our data so we make sure it fits into the fully connected layer. So we view it -1 to retain the same batch size, and then 5 times 16, as we previously discussed in the lecture videos for those calculations. And then what we'll go ahead and do is pass this through an activation function. So f dot rectified linear unit, self dot fc1, pass in x. Do the same thing here for the next one, self.fc2, pass in x. And then finally, we'll go ahead and return this. We call the logarithmic softmax function, pass in x with a dimension of 1, or along the first dimension, I should say. So go ahead and run that. Make sure you didn't commit any typos. But after you run that, you should be able to call the actual model. So if we run this, we can call the model and check it to make sure it's working. Next question is, what is the total number of trainable parameters, weights, and biases in the model above? So there's various ways you can do this. Essentially, you just need to get a list of the number of elements per parameter. So you can say for p in, and then the name of our model. So model.parameters. Go ahead and print p number of elements. So if we run that, we get back these results here. And if you want, you can then add them up. And once you add these up, you essentially get 42,050. And if you want, there's code that we set for you. If you don't want to add these up manually, you can run this count parameters function that we have throughout the lecture notebooks in this section that will automatically count this up for you. Okay, next, we wanted to define the loss function and optimizer. We'll go ahead and say our criterion is equal to NN cross entropy loss. And our optimizer, we'll set that to torch.optimatom, pass in the model parameters, and set our learning rate of 0.001 or 0.001. Set that up, and now it's time to train the model. So for this, you don't need to worry about tracking loss values or displaying results or validating test set. We'll just go ahead and train the model through 5 epochs. So I'll say epochs is equal to 5. Then for I in range, epochs, so for every epoch, what I'm going to do is grab a batch of data. So we'll say for xtrain, ytrain, and train loader. Go ahead and apply the model. So pass in the features into the model. So we pass in our x features into the model, and then grab the loss, call the criterion, we'll grab y predicted, and then y train, and then we want to update the parameters. That's going to be done through an optimizer call, 0 grad, go loss backward, and then finally optimizer step. And if you want, you can print an optional statement, but let's go ahead and run this and then wait until it's completed training. I'll fast forward in time until this is done training.